Okay, YouTube, this is my third and final video in my little module on properties of logarithms, in which we're actually going to talk about a property that we haven't mentioned yet and is one of my favorite properties. It allows us essentially to evaluate a log of any base. And so that is to say that our calculators, let me go ahead and get my calculator out here. Many times, of course, we want to take, say, the log base something of a number and find out what exponent would give us that. But the only two buttons we have on our calculator are either the common log, or what we assume to be a log, assuming it to be a base 10 here, or the natural log, which is our log base e. And so what happens in a situation where we're asked to evaluate, not say maybe the log of 2 or the ln of 2, but maybe what I want is the log, say, base 3 of 2. I want to do something like this. And so in a situation where our base is not represented on a calculator at all, what can we do? Well, what we can do is we can change the base. And so to change the base to either 10 or e, typically, is our goal. And so if that's our goal, change it to 10 or e, then the reason why would be because then we could actually do it on a calculator. So this change of base formula, we say that logs with any base other than 10 or e can be written in terms of common or natural logarithms using the change of base formula. And what this does, it allows us to write or evaluate any logarithm using a calculator now after we've seen this. So a little bit of freedom. So we say if a, b, and c are positive real numbers, and our base b is not 1 and our base c is not 1, then we would see that our change of base formula is given as this. And it says that if we would like to find the log base c of a, let's say c is some undesirable base such as 3, then what we could do is we could actually change that base c into base b. So what we get is this new quotient expression where we say log base b of a over log base b of c. So to point out a few things here, our expression on the left started with a base of c, and now we've changed it into two different, I guess, a numerator and a denominator expressions that have bases of b instead. So a and c, where do these come from? We can see that a really was the thing we were taking the log of in the first place, and c had been our base, our initial base, and is now just this underneath the bar here, or the denominator quantity, its argument. So essentially, if in particular log base c of a equals log base b of a over log base b of c, and as long as these two bases are the same, we get equality, then what you're going to see is in particular, we want to change log base c of a into log base 10 of a over log base 10 of c. And I'm going to fill that in here. These are both base 10. These are common logs. Or we could say that log base c of a is ln of a over ln of c. And in every possible instance, you can see that the a goes up to the numerator, or this thing that we were taking the log of in the first place is now the argument of the log in the numerator. And then the thing that was our base in the first place is now the argument of the log in the denominator. And so really, in every possible instance, we could keep doing this. And so what we get here is a situation whereas if I would have come back up here and recognized what my initial values were, this is what we were calling in our formula over here c, and this is over here in our formula what we were calling a. And so what I choose to do is to rewrite this in terms of a different base, and the base I might choose to do is base 10. So I could say this is log base 10 of our a-like thing here, log of a, and in this case our a is 2, and we would say this is over log base 10, okay, so same basis here, of our subscript here, 3. And so with this is something that we could easily go type into our calculator, log of 2 divided by log of 3. And so what that allows us to do is come up with the value for this. It says that 0.631 is approximately its value, 0.631. So I'm going to put a box around this. And what I want to show you is that this was equal, by the way, to log base 3 of 2. If we were to rewrite all of this in exponential notation, you would see that really what this says is 3 to the power of 0.631 is equal to, or at least I'm going to write approximately equal to 2. And so I just want to check this for us here. If we were to take now 3 to the power of 0.361, then you'll see that we get approximately here 631. That was my problem. Let's try that again. 631, because that was way off. We say then we get approximately 2, and only because we rounded our exponent here. So essentially we can get now a value for any of these. What I want to do then is just interestingly rewrite logs that we can evaluate into logs we can't evaluate using common logs and natural logs. So for our first example here, we have a log base 3 of 8. In other words, we're saying, 3 to what power gives us 8. And so previously, again, on a calculator, impossible to do because we don't have a log base 3 button. But if we rewrite this in terms of common logs, that would be just log base 10, log base 10, then what we would get here is a over c, where our a value, or our bigger number here, is 8, written bigger, not that it's greater than, but we would say 3. So to evaluate this, we'll just grab our calculator here. As a matter of fact, we just hit log 8, that divided by log 3, and what we get is about 1.893. So approximately 1.893. And just to check this, if this is approximately 1.893 here, we'll throw this back into our calculator and we say 3 to the power of about 1.893, and what we get is approximately 8. So for this second example, all this is asking us to do is to evaluate this but using natural logarithms. So just to show you, you don't have to rewrite every log in terms of common logs. We could also rewrite this in terms of natural logs. The only rule is that the log on top of this quotient has to have the same base as the log on bottom, and if that's the case, then we could just drop in our values here, 24 up top, in this case 6 on the bottom, and we'll go throw this into our calculator as opposed to common logs, and you would see that ln of 24 divided by the ln of 6. What we get then is the 1.774 value that you see there, 1.774. So in reality, what we're saying is 6 to the 1.774 power gives us approximately 24. So that's our change of base formula. That's why we use it, and that's how you use it. Cheers.